Wow, that took 20 minutes. Okay, so just really quickly, there's a lot of 1,4 addition reactions that are involved in polymerization reactions. So I wanted to go over this a little bit. I don't spend a lot of time on polymerization, but I wanted to show you how this works. So polymers are made up of monomers. And there's different kinds of mechanisms. This is cationic, there's anionic, and there's radical. If you go back into the radical reactions chapter, they give some examples of radical polymerization. So when you take isoprene and you initiate the reaction with a small amount of acid or anything to make the carbocation, so sometimes they'll use like a metal ion, and the metal ion will cause the first reaction to take place. Right. Which one of those two double bonds will react first? So we're going to have a positive ion as an electrophile, right? And if this double bond breaks, I'll have a carbocation here, and then by resonance I'll have one here, right? So this is secondary versus primary. If I react with this one first, then what happens? I'll have a tertiary, and then resonance puts the double bond here, and then I'll have a primary. So of the two, this is the more reactive double bond because of the combination of carbocations that it produces by resonance. Okay? So that means that's the lower activation energy pathway. So this bond will break, and what you end up getting is really slow internet. So whatever this, it can be a hydrogen, this could be a hydrogen, it could be a number of different things. Positive charge there, and then by resonance it does that. It's a double bond, although it doesn't look like one. And now you have a positive charge there. And then it reacts with another unit of isoprene. And again, this is a bond that's going to break. All right? And that'll form the positive charge will show up there. And then by resonance, this bond will shift over like that. Okay? So what you're seeing is the first unit produces a carbocation, and then by resonance converts to this, which is the thermodynamic product, or leads to a thermodynamic product because of the more highly substituted double bond. And then that carbocation attacks the next isoprene unit, right? And if it's done under conditions where you can get a thermodynamic product, then this is the product that you'll end up getting. That is, this will be connected to, let's see, did I do that right? Yeah. This carbon will be connected to here. That's the same as this one here, right? That's that branch there, and then you'll have this other group that goes like this. And again, this is the repeating unit of the polymer. And it's just based on what the monomer is. So if you have a monomer and you want to figure out the polymer, you just have to figure out where they're connected and then just repeat that over and over and over again. Okay. So the next topic to cover, we've already actually covered it in lab, and it's cycloadditions. So we're going to go over Dielsalder, and I'm going to skip a lot of the other stuff that's in the chapter. Okay. There's a lot of neat things, but Dielsalder is one of the more useful ones. So cycloaddition reactions, you need to know the definitions of what each one is, but you don't need to know how the mechanisms of all of them work. So cycloaddition, this is known as a 2+1 or a 4+2, depending on if you're counting double bonds, if you're counting pi electrons, okay? So in a cycloaddition, this is a concerted reaction. And all the electrons move at one time. It's an addition reaction in the sense that you've added this unit to the ends of this molecule. Okay. Now, one of the evidences for this reaction being a concerted reaction is the fact that if you change the solvent from very high polarity to very low polarity, the rate of the reaction is unaffected. So think about if you change the polarity of a solvent to be really polar, right, and it changes the rate of the reaction, that implies that it stabilizes charge in the reaction somewhere. And one of the evidences for this reaction mechanism being this way, that is, there's no charge developed during the entire reaction, is the fact that if you change the solvent, it doesn't seem to affect the rate of reaction. I mean, you could see there's possibly a lot of ways that reaction could have taken place. One is this has resonance structures. One looks like this. And if that was actually one of the intermediates in the reaction, changing the polarity of the solvent would have changed how fast the reaction goes. And if it was like that, then this pi bond would break here and this would form a bond here, right? So the fact that solvent doesn't have any effect on the reaction implies that there is no charge developed during the course of the reaction. There's two other reactions in this classification called pericyclic reaction. One is known as an electrocyclic reaction, where you have a set of pi bonds that literally rotate. And if you'll notice what happens in this electrocyclic reaction, it creates a sigma bond and causes what's called a ring closure. Okay? Because you have a system that's open, and when the pi bonds move, right, you form this ring structure. And then there's also sigmatropic, which simply means it looks like a sigma bond moves. Okay? So really quickly, going back to the cycloaddition reaction. This is the basis of the Dielsalder reaction. Generally speaking, delta H for this reaction is negative. Why do I say delta H for the reaction is negative? Yeah, if you look at it's a couple ways to do it. Pi bonds are broken and sigma bonds are formed. So if you count the number of bonds, like there's one, you could count them all or you could just count these guys. 1, 2, 3 pi bonds. Over here there's only, right, 1. And then here, if you count sigma bonds, there's 1, 2, 3, 4. But if you count over here, there's 1, 2, 3, 4, 5, 6, right? So what I've done is I've exchanged pi bonds for sigma bonds, and we know that sigma bonds are stronger than pi bonds. So overall, this reaction is going to be exothermic because the product is more stable. The presence of pi bonds, when we talked about stability of dienes in the last lecture, right? The presence of pi bonds indicates instability because you can hydrogenate those, and they release energy when you hydrogenate them. So there's fewer pi bonds in the system. As a result, delta H is going to be negative. So delta S for this reaction is also negative. Why is delta S negative? Yeah, forming one thing out of two things, right? So Delta, which of these two favors spontaneity, delta H or delta S? Delta H, because exothermic, generally going to lower energy, favors a spontaneous reaction. Delta S, does it favor or disfavor spontaneity? It disfavors it because being more organized, taking many things into few things, tends to be less favorable in terms of spontaneity. So, if you think about free energy, trying to get my, this is going really slow, the iPad. Delta G is delta H minus T delta S. That's the term that changes with temperature, right? So let's say temperature was 0. This is the way I like to think in terms of extremes, okay? If temperature was 0, then delta G would have to be negative, right? So that means at low temperatures, this reaction is spontaneous. Let's say T was infinity, then delta H isn't important, right? Because then this T delta S term becomes the only important term if T is really, really large. Well, if delta S is negative, then T delta S will be negative, and minus, right, means it's positive. So that means delta G at very high temperatures will be positive. So at low temperature, the reaction is spontaneous, and at high temperatures, it's non-spontaneous. So it turns out going in this direction is known as the Dielsalder reaction. And this is known, and going in this direction is the retro Dielsalder, okay? Because it'll go in reverse at high temperature. So you take a system that looks like this with a pi bond, right? And you heat it to high temperatures, and you can force that ring to break apart in what's called the retro Dielsalder reaction. Generally speaking, the temperature is pretty high, because usually the product is so much more stable than the reactants. So temperature is usually pretty high. Okay. Let's see, do I want to go over all this? Oh, yeah. So in general, these what we call pericyclic reactions have 4 features in common. They're all concerted reaction mechanisms. All the electrons move at one time. Okay? The mechanism involves a ring of electrons moving around a closed loop, okay? Either starting in an open loop and forming into a closed loop, or starting as a closed loop in the retro Dielsalder and going back to an open. Okay? And then the transition state is generally cyclic. And then the effective solvent, I said already, usually doesn't have an effect on the reaction rate because the transition state isn't charged. Okay? I'm going to skip that. Okay. So this is a 4 plus 2 because it's 4, the way they're describing it's 4 pi electrons and 2 pi electrons. And it turns out to be one of the most important reactions in like pharmaceuticals in building larger molecules. So I always tell students that if you're going to go into pharmacy, if you're going to go into research, you don't have to remember all the details of a Dielsalder, just remember how it works, because what's going to happen to you later is you're going to see all these reactions in your pharmacy classes or your research, doing your research, that are based on the Dielsalder reaction. Okay? I literally had students call me up and say, you remember you told me about the Dielsalder reaction and how important it was, and I ignored you? I'm like, yeah? Oh, it's come back to bite me in the butt. I see it all the time. These are people that are doing research in pharmaceuticals and stuff. Yeah, you see it all the time. So it's not bad to just be able to recognize it. Okay? If you don't remember all the details, you don't remember all the details. Okay, so yeah, so it's a concerted mechanism. We talked about that. We often, in Dielsalder reactions, put a substituent on either the electrophile or the dienophile. So the dienophile is the thing that's not the diene. The diene is the electrophile. And then there's, anyway, sorry. So you know some of this already. So this is the diene, this is the dienophile. It means it likes the diene. We often put a group, a functional group, on that, at that position, because what it actually does is it speeds up the rate of the reaction. Okay? And that group can either be an electron withdrawing group or an electron donating group. So it just depends on, well, I'll show you. It depends on how you want the orientation of the molecule to end up. The transition state for something like this, it's kind of like you would expect. Hang on. It looks like this because it's a kind of a concerted reaction. You can draw all the electrons delocalized in a ring, sort of like it is in benzene, between all the positions where the electrons go. And it doesn't matter which way you draw the electrons going. It can be either clockwise or counterclockwise. We already talked about this. The products generally have lower free energy simply because we're exchanging sigma bonds or pi bonds for sigma bonds, and sigma bonds are more stable. So an energy diagram for this reaction looks like this with a single hump because it's a concerted reaction mechanism. So like carbocation reaction mechanisms involve a second hump because you have to form the carbocation and add the nucleophile. I'm going to skip this slide. I already mentioned this. Man. They made a lot of slides on it, and you can read these, and hopefully they'll all make sense to you now. There we go. Okay. So, to make, like I said, to make the reaction faster, what happened, guys? I just skipped all those slides. Are you eating a carrot? Oh my God. That looks like an organic carrot.
Came out of my backyard.
Yeah, okay. Dog fertilizer carrot?
No, cat fertilizer.
Cat fertilizer. I used to... I have to tell you a gross story. When I was a child, we used to play under this tree, or we decided we were going to play under this tree, and it's where all the red mint grew. And my grandmother used to hate it when we would play in there because the red mint is what she would use to make a lot of Japanese foods. And so we'd get in there and we'd get all muddy, and then she'd yell at us. One time we were in there digging around, and I don't know what we were thinking. We shouldn't have been playing in there, but we were in there. We were little, like 5, 6 years old. But I clearly remember digging in there because of what happened right after that. We were filling it with water, and we were burying trucks, and we were pulling them out, like Discovery and all that kind of stuff, because we didn't have like video games. My uncle walks by and goes, Hey, you guys know that's where the dogs all go to the bathroom, right? It's the last time we played under that tree. Because the dogs were all chained up next to that tree. We were just like digging around in it. It's disgusting. But man, that mint, it grew like crazy. And the persimmons that were on that tree, that was a persimmon tree. Man, those are the best persimmons. Now it's a very old tree. It's still there. I see it, and I go like, oh my God, that's that tree. All right. Yeah, so we often attach groups in the position where we showed X before because it helps to speed up the reaction. It also helps to orient the way the Dielsalder adduct forms. So I'll talk about that in a second because it's not in your book, and so I wanted to mention it to you. Okay, so this is an electron withdrawing group on the dienophile. The question is, how is an electron withdrawing group? The way you show it is you show it by showing resonance structures. So for example, if you were to do that, that's an electron withdrawing effect. That is, it's pulling electrons away. What you're left with, I'm going to draw it over to the right here, is you're left with something that looks like this. And then there's resonance structures like this. That's an electron withdrawing effect. And typically you can identify electron withdrawing effects because they all look like this, okay? And what I mean by this is that they have a double bond that's conjugated to the system, and they have a more electronegative group on the other end of that double bond. So it pulls electrons out. It's both an inductive effect, but primarily it's a resonance effect. So why would this make the reaction go faster? Because it gives more of an incentive for the diene to push electrons into the dienophile. So if there is a partially positive charge here and a partially negative charge here, these electrons will draw this direction. At least that's the concept. You all right?
Yeah, I just have time to burn for the next class.
All right. Okay, so again, electron withdrawing effect, oxygen. Cyanide is a nitro group. If you think about what that is, it's like that, right? So it can draw electrons up to the nitrogen being more electronegative. So a CN group is a C triple bond to nitrogen, right? And that can also draw electrons up in this direction like that. So again, it's an electron withdrawing group because it has that carbonyl group, or C double bond to something more electronegative group next to the double bond. Okay. So I want to show you something. Let's see if I can remember how to do this because it's been a long time since I've done this. And I didn't make a slide for it. So what I'm going to do is make a slide for this. So let's make my diene look like this. So I made that too small, hang on. I zoomed in too much. Well, that's okay. Here's my diene. And now what I'm going to do is I'm going to put an oxygen here. But the key is it's something with a lone pair of electrons on it. Okay? Lone pairs. This is an allylic lone pair, right? Remember allylic lone pair, that pattern we talked about over and over and over and over again? It's a pair of electrons attached to an atom on the double bond. it's an electron donating group. And by resonance, if you draw the resonance structures, it'll do this. It doesn't distribute to the other double bond. It only distributes to the one, okay? And what that does is it gives me a structure that looks like this. Like that. Okay, so now, we just talked about putting an electron withdrawing group makes it go faster, right? This also helps it go faster. And if I have this as my dienophile, where's the partial positive charge in the structure? It's at the very bottom, right? It's down here, like that. And you notice that in this structure, that the dienophile could actually be two different orientations. It could be like that, or it could be like that. Which one's preferred? The first one, right? The first one, because the positive and the negative charge in the resonance structures or in the electrostatic potential maps or in the electron charge distribution, however you want to say it, the partial charges line up with each other. So there's a preference for this molecule to form the adduct. It's called the adduct when the two come together, with the charges aligned so that they're most favorable. So the major product for something like this, there's two possible products, but the major product is this one. Like that. The double bonds will shift, and the new bonds will form like that. Okay? That makes sense? Like how that works? So in order to tell the alignment, you actually have to look at the resonance structures and look at where the partial negative and the partial positive charges go and line those guys up. If it's symmetric, it doesn't matter. One of the compound that we used the other day in lab, we didn't have to make this consideration. We used maleic anhydride. Right, there's the two with electron withdrawing groups. It looked like that. And because it's symmetric, it doesn't matter if it's right side up or upside down, it just adds. Okay. Questions? I'm trying to visualize it in 3D right now. My brain hurts. Okay, so oh. Okay, so here's the other thing to consider. Your dienophile, that is your single double bond, your dienophile. The groups that are attached to it can either be in a cis configuration or a trans configuration. And when you're done, you're forming a ring, right? So when you form the ring, these two groups, and especially this one's symmetric, these two groups could be either up or they could be down, but they have to be together. Okay? Now this molecule is symmetric, so it doesn't matter. But the group can be either upwards or downwards. Right? If this wasn't symmetric, then you would end up with this either going in the upward direction or the downward direction. But they have to, the key is, if it's cis, they have to come together. If it's trans, they have to have one being up and one being down. So as this bond forms here to here and here to here, one of those groups has to be up, one of those has to be down. And because it could either be added like this or flipped over like that, then you end up with a pair of enantiomers of each other. They'll be mirror image molecules. Okay? You're trying to visualize that in 3D. Right? So hands are always helpful, right? So you could actually draw this thing on your hand, and you could say, here's my diene, here's my dienophile, and you can, on your hand, literally draw, I should have done it with my other hand. It's like that, right? And here's the diene, and when they come together like that, with one group up and one down, right? If it comes together like this, now you can't see it, but it's drawn the back of this molecule. If I had drawn it, this is down, right? So here, it's up on this finger, right? Here, if I do it like this, it's down, because it's this one that's facing it. So you know, if you really want to, you can draw this on the back of your hand, but you might have to have a friend help you draw that. Or you should use your right hand to draw. So there'd be trans, and if it goes like that, because the groups are in the opposite direction, right, it's a pair of enantiomers. All right. Chemists do a lot of drawing on their hands in organic chemistry. Triple bonds can also act as the dienophile, again with the electron withdrawing groups on it. The electron withdrawing groups, right, here have to be in the plane with this molecule, because what happens is when this bond forms, right, only one of the pi bonds reacts and the other one stays. So in the mechanism for this, you would draw it like this. The bonds that you form are here. I don't know if you can see it. Like that. But since you're only reacting one of the pi bonds, there's two pi bonds here. Then one of them's left behind. So now that molecule on that end is flat. So all of these are in the same plane. Okay. So let's try to draw the product for this reaction. And recognize there's two possible products, all right? And then we'll do a retro Dielsalder. I'm going to draw them on the board because it'll be a little bit easier for me to do it on the board. Let's see. So the first thing that you want to do is draw your diene and your dienophile in an orientation where you can close the ring. So I've shifted it over, right? So this is facing this. This is going to form the new ring system. So all I've done is rotate that and turn it to my liking, essentially. I have a sigma bond here, so I rotated that. So now, it's going to form here. And so this is going to rotate like that. And you end up with, let's see. So let's see, let me try to do this so it's easier to see what's going on. That's a new bond, that's a new bond, that's a new bond. What's the other possible orientation?
Wouldn't there still be a methyl group?
What am I missing? Oh yeah, there's one here. No, that's that one. There's these two. What's this one? Oh, this one I'm missing. What's the other possible way it would add? Upside down. So I could take this and flip it over, right? And so it'll be like this. Draw the 6 degree. These groups will be up here. This will be down like this. That, and that. So let me ask a question. Which do you think is probably more favored? Yeah, there's not actually like there's supposed to be, I don't have answers for these slides by the way, so, but I think there's, one of these two is actually more favored than the others. Or at least I don't have the answers to these slides.
So there's a partial positive.
There's a partial positive charge here. This methyl group might, if it was an oxygen for sure, there would be an orientation to it. Methyl groups are still electron donating though. So that means if you put higher electron density onto this bond, then you can think of it as partial negative charge over here because of the electron donating effect of this methyl group. So there's more charge. It's not a strong electron donator, so I'm not sure there's a real preference. But there's a electron donating effect here, right? And because of the electron donating effect, it may cause this molecule actually to orient in this direction. But those are some of the, if it had been an oxygen, for sure it would have flipped over, okay? But because it's just like a moderate electron donating effect, might not be. And then what you'd probably have to consider is like the steric effects, because here you have more large groups next to each other. So it might orient it in the topward direction. Okay, but those are the things to consider. So to make your life easier when you're given a problem like this, draw the diene and the dienophyte in the shape of the ring that they're going to form, okay? And then just draw the product based on that. The way they've drawn it there, it's really difficult because they've got it, right, in a weird orientation, so I just redrew them. Okay, so we're going to do a retro Dielsalder. Oops. So the CN, that group, the nitro group, or nitrile group, is part of which molecule usually? It's the double bond, so it's part of the dienophyte, right? Not the diene. It's electron withdrawing group. It's part of the dienophile usually. So if you want to know what the Dielsalder product or reactants look like, right, you have to remember that when this thing formed, those are the sigma bonds that form next to the dienophile. So now that you've drawn the line there, you can just move the electrons backwards. This will go back, this will go to here, and this will go to here, like that. Now there's already a pi bond present there, right? So that means it becomes a triple bond. Like that. So again, when doing the Dielsalder, line up the double bonds or the triple bond and the double bonds so that you form the ring. When you do the retro Dielsalder, you have to figure out which one's the dienophile. Sometimes it doesn't matter, so you can split it either way. But once you figure out what the dienophile is, you just draw a line, right? And then move the electrons backwards. Break the sigma bonds and form pi bonds. I think this goes without saying, but maybe it doesn't. For the Dielsalder reaction to work, the double bonds have to be in the S-cis configuration. Somebody asked the other day, and I thought I would just mention it here. When we have S-cis and S-trans, we don't use that in the nomenclature. That's just a description of the orientation of double bonds. You don't ever have to say 1,4-butadiene, S-cis, 1. You don't have to say anything like that. You don't have to add cis and trans or E and Z or something like that to the name when you're doing the nomenclature. So we have S-cis and S-trans. The bonds have to be in the S-cis configuration because if they're in the S-trans configuration, that's too far away for the electrons to travel in a circle. Okay. So like if this is your diene and this is your dienophile, you can't close the ring from here to here. They're too far apart. Okay, so a little bit about cyclopentadiene. So you guys are familiar with this reaction. This is very similar to the reaction we did the other day. Right, this, to make this the same, I mean what this is, what this is this. To make this the same as the reaction we did in lab the other day, all you would have to do is erase those guys and then connect them like this. And then it's the same reaction. Okay? So this is the same reactants and products. Or same reactants essentially that we had for our lab the other day. So there's actually two possible stereoisomers for this one. And when this ring forms, I think the simplest way to draw it is like this, by the way. Oh, sorry, that's not double bond oxygen. Let me start over again. You're still going to have the 5-membered ring. That's where the double bond is. This we usually draw in the upward direction, so you draw a wedge. And then these two carbons are this carbon and this carbon respectively. Okay? So then I have to just draw the rest of the molecule on it. Because they're cis with each other, they can be either up or they can be down. So in drawing the two possible product molecules, let's do this. The pen's acting funny. This can be up, and if that one's up, the other one has to be up because they're cis on the original molecule. Like this, or they could be down. So I'm just trying to write that out as CHO because I can't seem to get this thing to draw like that. So those groups could be either up or down. Now down, you guys remember endo and exo, right? Endo is towards the large side of the bicyclic structure, okay? That means towards this part of the molecule. So if you think about how this is drawn, okay, these guys are on the same side of the bicyclic structure as this larger side of the molecule. This is the smaller side of the bicyclic structure, okay? That's the endo side. And this is the exo side. And if you remember, if you think about in profile what this molecule looks like, that's where the CHO is in retrospect to, or in perspective to where that group is. If I put a circle there, right? That's the bridge. And then this is the C double bond C. So this is endo. The other one actually looks like this. And this is exo. It's exo because that group is away from the larger side of the ring. And we talked about in the handout in lab, this looks like a U, and this looks like a Z. Okay, so with cyclopentadiene, okay, see, I can't draw like this. So this is what they draw. This is the endo side. It's on the same side, away from the bridge, same side as the larger bridge. And the exo is on the same side as the smaller bridge. Okay. Endo is the preferred configuration for these reactions with cyclopentadiene and a dienophile. So where you can have orientations of the dienophile based on charge of the groups, like the electron withdrawing and electron donating groups, you can also have orientation based on whether or not it adds in the endo direction or the exo direction. And endo turns to be the preferred side. And without going into all the details that we went into in the lab, because you guys were all in the lab, it has to do with molecular orbitals and the way they line up. And the molecular orbitals for the endo form, they have a better alignment, and as a result, right, the major product for this reaction was the one we started, is the endo product. These are the ones going down. Again, this is that side of the house, and this is like one part of the house over here, and this is part of the roof line over here. Okay. Again, has completely to do with how the orbitals line up. One way to illustrate it is something like this. Right? That in the transition state, it actually looks like this. This is known as the ADA, where they're just sitting on top of each other. This group is underneath this. And when we did the simulations, if you remember, the molecular orbital actually for this extends over here and here, and it lines up with these molecular orbitals over here. When they come together, because the orbitals line up better, it's a bigger pipeline for the electrons to flow through, and so the reaction goes faster. And hopefully that's what you got out of the lab. Did you guys get that out of that lab? Endo and exo? Yeah? Okay. All right, so I'm going to skip over all of this. I usually spend time talking about all of this, and it's very cool. I think I'm done with this chapter. I just want to make sure, yeah. This is the details of UV vis. Oh, look, there's the color wheel. How your eye works. Yeah, we're done with that. Okay, hang on. Yeah, I'm basically done.